So the theme of this particular video is what happens when matter fails and falls apart. And there's three basic ways that an atom or an isotope can decay into something else by failing. So we'll start with the least glamorous, which is beta decay. And beta decay is called beta decay because it has a beta particle released as a result of the decay. And that beta particle, after a bit of research, was determined to be just a high-speed electron. Okay, so suppose you happen to be a hydrogen 5, just minding your own business. Hydrogen 5, let's make it a hydrogen 4. Minding your own business. Okay, so I'm going to draw that for you. Hydrogen 4 has 1 proton in its nucleus and it has 3 neutrons. So for whatever source or reason that is not stable, see above regarding strong and weak nuclear forces, that thing isn't going to stick around. So what happens inside of that nucleus is one of your neutrons decides that it doesn't want to be a neutron anymore, and it splits itself into 2 pieces. So this neutron, minding its own business, splits up like so. Now the thing about splitting a particle is all the properties that it had here have to be conserved. So the mass of this thing and the mass of this thing have to add up to the mass of that, more or less, because we do lose some energy when particles subvert, like we did in the fission and fusion video. The other main feature of a neutron is that it's charge neutral. So if these 2 particles come out of here, then they either have to be charge neutral or they have to be charge balanced. And the idea about beta decay is that one of these things was an electron. Okay. So if one of them is an electron, then the other thing has to have the same amount of charge that the electron has, but in the opposite polarity, so that these 2 things are charge neutral. And if the mass has to be conserved, electrons are very, very tiny compared to neutrons, so the bulk of the mass ends up here. So I need a particle that is approximately the same mass as a neutron, but has the opposite charge of an electron, and well, that's what a proton is. So during beta decay, what happens is that one of these neutrons, let's say this one, let's color it in pink here. This neutron has decided that it is tired of being a neutron, so it becomes a proton. This proton was already there, this neutron was already there, this neutron was already there. And in order for this neutron to subvert to a proton, fire out a high-speed electron. So if you look at what's left then in my pile here, I have a nucleus that has 2 protons and 2 neutrons. So that is still a, I guess I shouldn't put an H down there. That is still a 4-particle nucleus, but 2 of them now are protons. And if I check my periodic table, a nucleus that has 2 protons is named helium. So what I have here is that an unstable hydrogen, because it has too many neutrons, decays by beta decay into a stable atom of helium. It's a sort of natural process. If something gets created like this, either through a fusion or fission process or some sort of neutron collision between a normal hydrogen and this sort of thing, when that atom appears, a clock starts ticking, and once the half-life goes by, right, half of the atoms here will have undergone this process, ejecting a high-speed electron and subverting one of their neutrons into a proton. Okay. Next one, alpha decay. Which means an alpha particle is ejected. Okay, now an alpha particle turns out to be a helium-4 nucleus. Okay, so that means it's 2 protons and 2 neutrons. So if I were to grab something like, let's see, thorium-228. Okay, so thorium is number 90 on the periodic table. Thorium-228. I'm just going to check that. So, thorium is number 90 on the periodic table. That means it has 90 protons and the remainder of those particles is 138 neutrons. I am not going to draw those for you. So if thorium-228 undergoes alpha decay, what you end up with then is a particle that has shed 2 protons. It's not 90 anymore, now it's 88. And it has also shed 2 neutrons. So instead of 138, it will be 136 neutrons, 136 neutrons, and 88 protons gives me 224 particles. Notice that this number has dropped by 2 because of the 2 protons. This number has dropped by 4 because I've shed 4 particles. So if I were to go and I were to search my periodic table for atom number 88, I believe that you come up with Ra, which is either radium or radon. Let me check that. Okay, so that's radium. 2, 2, 4. Okay. So this is quite common. This is not. This is a much higher energy exercise. You can see that the mass of this, like a proton is something like 1,000 times heavier than an electron, and there's 4 of these. So there's 4,000 times more mass being ejected during an alpha decay than there is during a beta decay. This has also required the nucleus to break a little bit so that this chunk can come flying out. It's also a highly positive charged chunk right next to a highly positively charged nucleus. So the electrostatic repulsion between these 2 pieces is quite large, so it's going to get fired off. Whereas up here, this nucleus remained whole. There were no bits flying off the nucleus. There was simply an electron cooked up into space. And with the energy difference between neutron and proton plus electron, it was able to be moving a little bit. Notice that the extra pluses here are going to try and drag that thing back to slow it down. So this one is less energetic. It's much more common. This one, only a very specific set of atoms atoms or isotopes are capable of undergoing this type of decay. So the third type of nuclear decay is the really spectacular one, where some amount of the nucleus simply pops off as energy and starts releasing gamma particles, which are just high energy light. So those things are highly radioactive, very unstable, and are not something that we can sort of track. So we're going to do what's called the decay series, where we take a natural isotope, something that you can find in a rock like this, and we track its alpha and beta decays until we get down to a stable element. So I'm just going to clear this off and we'll give one a try. Okay, so to carry out this exercise, we need to have a few things. So first off is a copy of the page that's just below this video. And the beginning of that is a set of instructions for how to do this. And then there's a teeny tiny list right here of things that are alpha particle emitters. So you're going to need that in mind. The rest of the list, you can see there's a whole bunch of them, are elements that are stable. There's about 206 known stable isotopes of materials in our universe. So the basic assumption here is that anything that shows up in this list that is not an alpha emitter or stable is a beta emitter, right? So we're going to follow this thing, which is not on our stable isotope list, and we're going to track it through in order to see all the stuff that gets generated as it decays down to a stable state. So first thing I'm going to do is I'm going to look for AM241 on my alpha emitter sheet, and indeed it is there as an alpha emitter. So when it emits an alpha particle, I can maybe put a little alpha beside that, it's going to shed 2 protons and 2 neutrons. So that means it's going to end up as something with only 237 particles in its nucleus, and the protons will have reduced by 93. And so if I look up the chemical with 93 in the periodic table, I get neptunium. So this americium 241 is now neptunium 237. So I'm going to check on my periodic table to see if neptunium, or sorry, my list to see if neptunium 237 is an alpha emitter, and indeed it is. So it's going to go and it's going to do it again. It will shed 4 particles. 237 minus 4 will be 233. 2 of those will be protons, leaving only 91 protons left. So number 91 on the periodic table is Pa, palladium, I think. So again, I'm going to look up Pa233. And I do not find Pa233. Pa231 is an alpha emitter. So I check my stable isotopes list, and palladium is not one of them. So this thing undergoes a beta decay. Now if it undergoes a beta decay, the number of particles inside its nucleus hasn't changed. All that's happened is that one of the neutrons has become a proton. So there's an extra proton sitting inside that nucleus. And if I check number 92, 92 is good old uranium. So this lump of americium has become neptunium, and then neptunium became palladium, and then palladium became uranium. These nuclei are sort of dancing around, changing into different atoms as it breaks apart. Now you've noticed I've written it in a funny kind of way. The way I'm structuring this is that anything that is americium goes in this line. Okay? Anything with 95 protons. Anything with 94 protons will go in this line. Notice I haven't generated anything like that yet. Anything with 93 protons goes in this row. 92 protons goes in this row, 91 goes in this row, etc. And since protons are what determines what's in this row, then anything in this row is going to be a neptunium, anything in this row is going to be a uranium, and anything in this row is going to be a palladium. The one that's missing, 94, if I look it up, is plutonium. There's a fun one. Okay, so continuing on with my process, I'm going to look up uranium-233 in my alpha emitters, and indeed, it emits an alpha. So that's going to drop down to this row. Skips over there. If it sheds 4 particles, I'll be down to 229. And if it sheds 2 protons, I'll be down to 90. So notice that this is in the row for 90 protons, and things with 90 protons are called thorium. So it's thorium-229. If we check thorium-229 on my list, it is indeed an alpha emitter. I hope I don't run out of space. Shed 4 particles, I'd have 225. Shed 2 protons, I'd have 88. Anything with 88 protons is hard to find. Ra. Radium. Okay, so I'm going to check for radium-225. Radium-225 is not an alpha emitter, so it must be a beta. If it goes to this row, it still has 225 particles in its nucleus. One of those neutrons has become a proton, so there are now 89 protons, which is why it's in the 89 row. And anything with 89 protons is AC, actinium. So I'm going to check actinium-225. And indeed, actinium is an alpha emitter, so I'm going to come up here, start a, what is that going to drop to? 2. What am I doing? 225, 89, actinium. That's an alpha emitter. Shed 4 particles, I'd be at 221. 2 of those are protons. I'm at 87. Anything with 87 protons is also hard to find. Francium. Probably francium. Okay, so I'm going to look up francium-221, which is an alpha emitter. So it sheds 4 particles, that would be down to 217. 2 of them are protons, so that's 85. Anything with 85 protons is an astatine. So you move AT217, which is an alpha emitter. There are a lot of, remember at the beginning I said that these were rare. Apparently I'm in alpha emitter neighborhood here. So it'd be 213. 2 protons would be 83 protons left. Anything with 83 protons is a bismuth. So I'm going to look up bismuth-213. It is an alpha emitter. Take 4 more particles out. I'm at 209. 2 of them are protons. That's 81. And 81 protons is tellurium. Okay, so I checked this one. Tellurium-209 is not on my alpha emitters list, so I'm going to check for, oh sorry, it's thallium, not tellurium, thallium. Thallium-209 is not stable, but it's not an alpha emitter, so it must undergo a beta decay. Still 209 particles in there. One of these neutrons has become a proton, so it's 82. Anything with 82 protons is lead. That's encouraging. And lead-209 is not stable, but it is not an alpha emitter. So it must undergo a beta decay. Still 209 particles. My face is clearly in the way. One of these protons is, or neutrons is now a proton, so that's 83. 83 protons is a bismuth. Bismuth 209 is an alpha emitter, leaving me with 205 particles in there. 81. That's a thallium 205, and thallium 205 is stable. Okay, so if I find a place for my face over here, maybe. I started with this particular atom here. So if this were to be created in a supernova or some sort of nuclear reactor and it just came to be, and you left it alone, eventually it would undergo an alpha decay and become this, neptunium, which would eventually undergo alpha decay and become this, which would ultimately go over beta decay and become uranium, then thorium, then radium, then actinium, then francium, then astatine, then bismuth, then thallium, then lead, then bismuth, then thallium again. And once it reaches this place, this nucleus is now stable. So when you read about nuclear waste, and you read about it becoming safe after a while, it has to undergo this process, right? Every bit of radioactive waste will inevitably work its way down through this natural process to something that's stable, and this is no longer radioactive. Unfortunately, you can see all these steps. Some of these steps take a matter of minutes. Some of these steps take hundreds of years. Some of them take thousands of years. So depending on which place you start at, you could be waiting a long time. So there's an example of this on there. It's a little more easy to read. It's posted up on the website. You can take a look at this sequence, follow through, and then there's two right underneath it that I've asked you to try yourself. Good luck.